Dear colleagues, welcome to meeting of our scientific and technical webinar, Critical Computer Technology and Systems. Our meeting today is 2003, beginning on 2001st year. Hence, next year we will have 25 years of our seminar. The topic of our meeting today is very interesting. It is cybersecurity and cyber resilience in the age of communication system and artificial intelligence, challenges and solution. As usually, I would like to underline that our seminar is organized on the base on our National Aerospace University Harkovy Aviation Institute Department of Computer Systems, Networks and Cybersecurity, and Harkovy Regional Center Industry 4.0. Information support of our seminar is provided by our Ukrainian Scientific and Education Society. And project on the implementation and development of European Digital Innovation Hub in Eastern Ukraine. Hence, we can go ahead with our topics today. Before start of our seminar, I would like to congratulate all participants with day, very important day in our history of Ukraine, Happy Dignity and Freedom Day. And before start of our program today, I would like to present information about our industrial control system. It was a very important and interesting project, Cyber Edu. Coordinator of this project was Professor Oliver Popov, and very nice to meet today on the platform on our seminar. 2 months ago, I participated in the PhD defense by Elias Said, and Dr. Elias Said today is one of our reporter. Hence, congratulate Elias you once more, and congratulate your supervisors, Professor Oliver Popov and Dr. Frederick Blix, with your very important event in your life, and it was really interesting and scientific, deeply scientific words. Hence, we have good point for our future cooperation, and today we have a few reports. First one, I would like to invite Professor Oliver Popov for introduction words. After that, next presentation will be made by Dr. Elias Said from Department of Computer and System Sciences, Stockholm University. The topic of this presentation is cyber resilience and age of connected systems. As we agreed, time for this presentation is about 30 minutes. And the next presenter, Ivan Rябко, is a radiophysics engineer from Radiation Safety Department, State Institution, National Children's Specialized Hospital, Ohmedit. He is a PhD student of our department as well, and his topic is AI/ML methods for providing cybersecurity of medical web systems. Ivan will be talk during 20 minutes, and the last point of our today program is my 5 minutes traditional information about our events and next conference in this year and in next year. Hence, if you agree with such a program, it's my pleasure to invite for introduction words Professor Oliver Popov. Thank you once more, Oliver, for your participation in our today meeting and for your providing of our department, our university, and our country as well. Hence, it's my pleasure to invite Oliver for his introduction words. Welcome.
Thank you very much, Lala. I'm very happy to be with all of you. Can you hear me well now?
Yes, of course. Now is okay. Absolutely. Yes.
Yeah. Well, there is a difference between hearing and listening, but that's another story. Okay, I'm sorry for the glitch that our meeting started with. I don't know the reason why. Maybe I'm not so much experienced with Google Meet because I usually work with Zoom and Teams, but mea culpa, you know, my problem and my apologies, and really delighted to be with you here, you know. I will not take so much of your time, but I will take the liberty to introduce my department since I'm first time guest at your university and in your department. Just say a couple of words. I have a much longer presentation, which I will not take your time from it, from the seminar and so on, but I will say a couple of words, you know, about a little bit about our history and what we are trying to do. Okay, so let me just...
Yes, okay, welcome.
Is there any problems, Slava?
No, always okay.
Okay,
no.
Fine.
Okay, yes, please continue.
I would just like to share my presentation with you, a couple of things that might be interesting. Just, can you see my screen?
Not yet, but waiting for.
Okay. Okay. Let me just check. Okay. Can you see my screen?
Yes, now please share your presentation. We see your screen, yes.
Just a moment. I don't know what's going on, but it's no, I would like to share my presentation. And is everything okay now?
Yes, absolutely.
Okay.
Welcome.
So I think I have some kind of Ukraine in the beginning, you know, КриКТехС seminar or whatever, КриКТехС seminar. But as Slava said, my name is Oliver Popov. I'm with the Department of Computer and System Sciences at Stockholm University. And this is our first lecture, or not lecture, but maybe seminar at in your department. And it's a very germane topic, actually, very suitable, because the idea is to present something about the resilience And many thanks to Professor Karchenko and his colleagues for allowing us to participate in this seminar. The reference to resilience, it's obvious, you know, is more than appropriate and symbolic. The history of Ukraine is a history of resilience, literally up to the present, and still is, you know, about this kind of resilience through centuries and through many years, you know. And we hope that our collaboration is part of this civilized or effort, the civilized nations, you know, for perseverance and resilience in Ukraine. The Department of Computer and System Sciences is made up from actually five units, you know. One is the called Unit of Act and Communication with Technology, although it's the technology is in the name, it's not only the technology and so on. The other one is about information systems. The third one deals more with learning, different models of learning, using AI, using even machine learning, and for certain pedagogical paradigms and so on. The third one is our unit. I'm saying our because both Elias and I are members of this unit. It's called the System Analysis and Security Units, and it deals obviously about different type of systems and also, of course, security along with forensics or digital forensics. And also in this unit, you're going to see that the part is the machine learning, certain parts of artificial intelligence, and so on. And the fifth unit is something in the tradition of Sweden. I would like to mention it because it's part of the Swedish effort to help the developing regions all over the world, and sort of international character of the Department of Computer and System Sciences. It's a short name for a Swedish program for international development, and basically ICT in emerging regions. And it's a center which exists. Formally, it was established along with KTH 21 years ago, but many of the activities exist almost 40 years in the unit, and we have promoted a large number of PhDs. There is even a special PhD program within this unit. It's called Sandwich Program, where the student that becomes a PhD student in our department spends 6 months in our country, Sweden, and then 6 months in his own country, and that's the reason it's called a sort of a sandwich program. Historically, it's the first computer science department in Sweden. It was established in 1966. It was a joint effort and a joint endeavor with KTH, or Royal Institute of Technology. It still is in some areas. We still cooperate, of course, and there is a sort of, I call it a Holy Trinity alliance between Karolinska University or Karolinska Institutet, KTH, and Stockholm University. Even this alliance actually might be even a basis for forming something which is vaguely called Swedish University or whatever. And it's the largest department of computer science in Sweden, along with, and probably among the best five. I'm not going to say the best one because there's in some other areas excellent schools, but I will actually like to mention Uppsala University, KTH Lund, and also probably Chalmers University and Linköping University among the 5-6, you know, which are premier schools. Okay, our system analysis and security units is divided on four different sub-units. One is decision and risk analysis. The second one is data mining. Everybody these days has an AI because it's like a salt in a food. You know, you have to put it everywhere in order to be relevant and to be interesting. But so there is a lot of AI going on among these subunits. Then is ours with Elias, cybersecurity and forensics. And then you have something which is called immersive networking, virtual reality, distributed computing, even some parallel computing, and so on. You have a graduate program. Slava is familiar. As I said, I'm going to send you the extended presentation about this, so you're more familiar, so we can hopefully cooperate in the future again, like this meeting and like the previous project, the convention site that I do, and I hope other projects as well. Then I'm not going to talk about the just a moment. Yes, something about the research. You can take a look. Forensic validation, protecting basic human rights and preserving digital evidence integrity, semantic representation and analysis of evidence, forensic analysis, performance evaluation of distributed process, and forensic evidence. Then we have a cyber trust models, which is very much associated with resilience, cyber system control forensic, cloud forensic, forensically sound investigation on the dark web, ethical and legal aspects, different kind of regulations and so on, like GDPR and the integrity of investigations. And I'm supposed to present today a little bit about Dr. Elias Syed, already has told. He enrolled in our department as a PhD student in 2019, actually October 1st, and exactly after 6 years, you know, he got his PhD on the 30th of September this year. As I said, Professor Karchenko was a member of Elias PhD grading committee. It was another occasion to meet and to work with Slava. Elias came from the University of Trento, and where he got his MS degree in computer science. As you know, this is a very good university in Italy. And after a couple of years with his stint in industry, he decided to return to academia. So most of us cannot. Once you try academia, it's very difficult to leave it. Many aspects and dimensions of the resilience. I think that we're going to talk about that today. And as far as I know, which will give you an opportunity also to ask Elias a few questions, you know, because I haven't seen his presentation. It's something in the tradition of Elias, either to send me his presentation 24 hours or 12 hours before the presentation or even after that. But doesn't really matter, I entirely trust him. And as far as he says, explores how organizations can evolve from reactive cyber defense to adaptive, which is actually change of strategy even, data-driven, which I have a problem little bit with, and self-learning security architectures. Finally, I would like you to think about something that has a more machine hardware aspects, like what is called the fault tolerance, and also the resilience, the difference between them, and the synergy between those two, where I think that fault tolerance is actually a subset of resilience. I would like to thank you for the opportunity, for your attention, not only to what I'm going to say, which was a little bit less interesting, but what Elias say. Enjoy the seminar, and I wish you best wishes for a peaceful weekend. Thank you so much for your attention.
Thank you very much for your introduction, for your
and sorry again for this unexpected and this kind of unforeseen problem with the microphone.
Yes, our seminar is seminar on critical system, and we need go ahead in any conditions. Yes, thank you once more for your introduction, for your information, for your cooperation, and now it's my pleasure to invite for presentation Dr. Elias Syed. Welcome, Elias.
Hello, good afternoon. Can you hear me?
Yes, we see and hear you.
Good. Let me share my screen. First and foremost, I would like to thank Professor Karchenko I'm honored to have been invited to your seminar and your department, and also happy Dignity and Freedom Day. So my presentation will be more on cyber resilience, adaptive systems, cybersecurity, the cybersecurity aspect of adaptivity or adaptive systems, but more or less, I don't know how much time I have, but let me share my screen.
Yes, you have about 25 plus minutes. Yes, yes, we see your monitor, and welcome, Elias.
Okay, good. So is it visible for everyone?
Yeah. Yes, you can start.
Yes, indeed, it is.
Okay, thank you again, everyone. I'm really honored to present my work. I have been working on adaptive security related to cyber physical systems for the last more or less 5 to 6 years. I have been working with Professor Oliver Popov and Dr. Frederick Blix, and my topic for today will be cyber resilience in the age of connected systems, where we have cyber physical systems, whether we can define it as part of industrial IoT, or if IoT are a typical example of cyber physical systems, but we'll see. So cyber physical systems are, I think they are more concerning issues when we come to the cyber security. Yeah, I don't need to already Professor Oliver Popov have introduced me very well, so I will immediately go to my talk. So I will start with a little bit story. I'm pretty sure that most of you are familiar with this kind of attack, this colonial pipe attack that has happened in 2021 in the US. This is one of the most critical cyber attack that has happened in the most critical infrastructure, which is this fuel pipeline. So this was ransomware that forced the shutdown of this largest US fuel pipeline. Because of this, a number of flights have been delayed and shortage of fuels, and many compromisations have been happened during that time. So this kind of attack, it sounds like a cyber attack, but when we come to see if this is really actually happening on the cyber world or on the application world, but we see that this doesn't threaten actually the data of the computer, but it could actually impact the critical infrastructure where people depend on. So this shows actually a typical example of a cyber physical system, where the cyber attack actually can go beyond the IT systems to impact the critical infrastructure, which cyber physical system is typical of that. But what do you mean by cyber physical system? Cyber physical system, in a nutshell, in a very clear way, it's the communication between the physical world and then the digital world. And the digital world is, of course, the cyber world, where we have the softwares, algorithms, and communication. The communication between the physical world, where in the physical world we have sensors, actuators, machinery, the environment itself. So this is the communication between these two components, or we can call them two worlds. And then we have these autonomous vehicles, the energy system, telecommunication system, healthcare system, and all these are actually an example or examples of cyber physical system. I'm not pretty sure if financial systems are also considered to be an example of cyber physical system. It's an academic discourse, but in my opinion, I still consider them as part of cyber physical system. So this CPS as they are actually critical infrastructure, so we need to take care of actually the resilience of these systems. Before we go to the cyber resilience in the age of connectivity, which is the cyber physical system, before that, in our research or the way we see cyber physical system, there is also human in the loop, of course. So with this human in the loop, then this threats, the cyber threat landscape looks like it has different components from the digital, from the physical, and then of course from the human aspect, which is we call them the social actors. So there is also a little bit controversial or an academic discourse on how to define cyber resilience. Recently, we have actually published, actually it's not published, but it's accepted in the Higgs conference, where we define the cyber resilience from two sides. From the academic side, what the academic people are actually defining, how they define cyber resilience, and also actually these giant companies, IEEE, ISACA, Cisco, EY, or IBM, all these, the non-academic actually, or the industry, how they define cyber physical, cyber resilience. And then we just merge these two academic and non-academic definitions, and then we try to come up with this abstract definition. So our finding shows that this cyber resilience actually can be defined as an organization or system's ability to anticipate, withstand, respond to, adapt to, or recover from adverse cyber events. This is to make sure that to maintain an operational continuity and, of course, consistently deliver its intended outcome. So resilience, something that's related to how the system anticipates, withstand, respond to, adapt to, and recover. These all are actually an instance or indicators of cyber resilience. This is how they defined it from both this academic and non-academic discourses. So we have cyber physical system, that's how we live. So our life has become actually changed because of this interconnectivity, the IoT devices, because they are also a typical example of the cyber physical system. But these are actually the issues that we have. Let me start by saying that the secret solution we have today, sooner or later, it will be obsolete. That's the secret solution or the secret mechanism we have today. It will be obsolete because of the new types of attacks coming, new types of attack vectors, threats, and so on. So currently, we have static and reactive security solutions toward this cyber physical systems. And also when we see actually the solutions or the security solutions toward this CPS again, most of them are actually, they focus on the cyber world, which is actually on the application software. I think most giant, I would say, scientists are actually, they are, this is like a never-ending process between the actors or the hackers and the defenders actually. The attackers actually, they attack and then having a lot of many aspects of attacking, using many aspects of attacking mechanism, and then defenders have their own defending tactics. But this play of state actually, it's a never-ending process between the attacker and defenders. So again, what we see in the state of the art, most of the frameworks, the tools are mostly, they are focusing on the cyber aspect when it comes to the security solutions. And then there are reactive mechanisms, and then they rarely actually incorporate these predictive methods, which is actually an adaptive one of the adaptive techniques. And then when we monitor actually security events in this in this CPS, where it has these three components or three realm or layers, most of the existing actually frameworks or tools are actually a single domain monitoring tools, which are actually less equipped for multi-stage cross-realm attacks of CPS. So the gap here is actually the social and physical components of cyber physical systems are underrepresented, and then we need to come up with a solution in order to address this research gap or this challenge. Of course, we have cross-realm vulnerabilities. Cyber physical systems, they came with their own specific vulnerabilities. So the vulnerabilities that you get on the cyber could actually negatively or positively impact the network layer or the infrastructure, even the human actor, the social actors. So I would say securing cyber physical system is much harder problem than securing this traditional software system. This is because of one CPS actually placed in an open, insecure environment, then that makes them actually a good source of, they become suitable or a potential actually attack surface for attackers. And we have also this commercial tools responsible for monitoring of events and proposing or producing security mechanisms, but they lack this interconnectivity where you have actually a comprehensive or a holistic approach. So, as I said, these social and the physical components are underrepresented. When we think of actually a security mechanism or a security solution for cyber physical systems to make sure that they are resilient, then we need to make sure that these three components are actually taken into consideration. So how do we make sure our cyber physical system or our critical infrastructures are resilient, or to make them resilient? Or of course, in security, there is no complete security, but we try to make them secure as much as possible because as there is no any complete secure system. So we proposed a multi-realm approach. First, to monitor incidents that are happening on the cyber, on the social, and then on the physical layers of cyber physical system, on these three components. And then once you monitor the security events, what do you do? Then you need to come up with a security mechanism, but of course the security mechanism needs to be proactive instead of reactive, which is actually static security solutions, which, as I said, they become actually obsolete having these new types of attack vectors. I will skip this one because this is the methodology how we designed, develop the tools, the frameworks. We call them this design science research approach. I think they are very good when you develop a tool, a framework, particularly actually software engineering oriented tools. This is in my opinion, this is a good methodology, but I'm going to skip this one first. So in order to approach the challenge, we came up with a framework called Asphalia. It's the name of our framework. It's responsible, it's a cross-realm security attack event monitoring. This Asphalia has 4 components. I put this graphical representation because I cannot actually put like in terms of like how the codes are actually running behind the system, but this is a good actual graphical representation how the tool, how the framework works. Probably I will give also a little bit example if I have time how the framework works, and then I will go also in a bit explaining this adaptive security and so on. So basically, we try to make it as simple as possible because a number of tools, frameworks these days are a little bit complicated to, to get it done or to implement something or to produce something is something else. But I think the most important thing, many times I will quote Oliver. He said that getting it actually done is something else, but getting it right is what's the most important thing. So I follow that motive. Actually, it's a good one to make it simple and then to get it right instead of actually making it complicated. And then so this Asphalia is, I feel it's understandable for anyone even without security background. I would say in terms of understanding probably. So it has 4 components. The first one is a vulnerability model. We have a component responsible to capture actually different threats. What is the threat? What attacks are coming? Are they sequential attacks? Are they parallel attacks? How these attacks are actually going to be captured? And then what is the target? This is actually an analysis of the critical of the assets. Is it a software? Is it a network infrastructure? Is it a social aspect? Could be related to this, for example, phishing email and so on. So this is responsible in order to capture the attack pattern, threat, and target. And then we have another component, part of Asphalia, which is AM, which is attack mechanism model. This model is actually, or model or component, this is responsible to capture different attacking strategies or different attack pattern mechanisms. If you assume yourself, if you consider yourself or assume yourself as an attacker, you have a goal, and then what are actually the mechanisms or the means in order to achieve your goal. So there are sub goals, what you call this in security, we call them security controls, sub security controls in order to satisfy your goal, which is actually attacking something. And then we have behavioral model. This is at runtime, which actually catches information or data actually behind the system, which is how the system is behaving under types of attack actually. So the system is under attack, and then the behavioral model is actually responsible to record the fundamental system behaviors that's under attack. And then we have another one in event model. This is actually, so sometimes people, they call it a log file. Well, it could be log file, but it's really hard to say that or to classify if an incident is security related incident or not, because incidents can happen, can be recorded in logs, in systems, and of course software systems or in CPS in different infrastructure, but getting it actually, if this event is really a security event or a critical security event, is something which we worry about. That is, this component is responsible for that, to record just the final level events. So basically, the Asphalia has these components. To give you a little bit in a graphical way, the examples, for example, assume that there is an attacker that wants to masquerade as a legitimate entity. So this is so Asphalia considers this, for example, as a threat. I'm just trying to give you a very simple, in order to demonstrate actually how the tool, how the framework works. So this is a threat. And then it could be actually, for example, in this case, we assume that the target could be the software, which is a cyber warlord or the cyber component, right? Let's assume with a very common technique. Actually, it's a bit tricky, but this is a common. People are aware of this, at least aware of these techniques. And then, even though it's a bit tricky, let's see that this is a phishing email. So for an attacker, in order to achieve his goal, then he could actually exploit phishing, right? So before we begin actually looking into different components of this system, so when you say phishing, probably it could be actually related to the social realm, right? The social component of, because in the social component we have actors, the business process, the people, the stakeholders, right? So all these are actually considered to be as a part of the social component, the social layer, right? So here, in this case, the social realm or the social component, or you can call it a layer, can be compromised. So as an attacker, in order to achieve this main goal, he can actually do different sub-goals, which is actually a refinement of the main goal, which is he could actually obtain the name and certificate to spoof the legitimate site, or he can convince the user to enter sensitive information, or he can use actually stored credentials to log into legitimate sites. But those are actually sub-goals for the attacker, because the attacker, he wants to use phishing technique, right? Phishing email technique. So in order to do that, of course, there are the activities. We call them actually tasks or activities, which are actually specific skills that's needed for the attacker, because the left side are actually high-level security attacking mechanisms, but these are actually specific security attacking mechanisms. It could be obtaining domain name that visually looks like similar to the legitimate site, or you can obtain a legitimate SSL certificate for the new domain, and so on, different T1 until T6. These are actually different activities that an attacker considers them in order to achieve the sub-goals G1, G2, G3, in order finally to achieve the main goal, which is actually G, just to compromise, of course, the software. In this case, when we see the activities, we consider them, this is a cyber realm world, actually. So the cyber realm, which is the credential theft, the fake site, these are actually, so here we can say that the cyber realm can be compromised. And then if this is compromised, of course, what do you do? What could happen? Network traffic can be rerouted, right? So this is actually compromised operations can happen. And then if something is happening on the infrastructure, then we consider this as a physical realm can be actually compromised, right? So, and then we have actually system behaviors, recording of events continuously, how the system behaves during this kind of attack. So this is to show you that something that starts actually on the social layer could cascade actually, or could impact the physical realm. So in the beginning, it sounds like, okay, this is happening on the social realm, but you know, the byproduct or the final impact is actually on the physical infrastructure. So what we can see, each and every layers or realm has their own specific vulnerabilities, and then actually they need specific security solutions. So something that happens in one layer so could actually negatively or positively affect the next layer and so on. So the first one about Asphala is monitoring incidents in different layers. Okay, you monitor events, and then what do you do next? So as an extension of Asphala, we developed a framework. Actually, this is a component. You can call it a component, since this is an extension part that has an adaptivity component. So this is a semi-automated adaptive framework. It's semi-automated because we need still human in the loop for validation and verification of the outputs. So this is a semi-automated adaptive framework. It's based on this predictive control, model predictive control from this control theory. And then it has two major components, which is adaptive security mechanism and evolvable security mechanism. Yes, CPS technique must move beyond detection, beyond Asphala. That means towards a predictive adaptive defensive mechanisms that evolve with the threat landscape. How? I'm not going to explain actually the business process here, because in our framework we validated or we evaluated using a medical emergency response system. So this is from the Seniority project. It's I think a bigger project related to, it has different threats, cyber attacks, incidents. This is the objective was actually to monitor the incidents and then to come up with a security, with a security mechanism that could actually address the problems that it has. So we thought in order actually before going to this monitoring, adaptivity, it's better to have actually the threat landscape, what it looks like, the business process. For example, in our case, medical emergency response system, we have different actors, doctors, pharmacists, patients, and then the different actors. And then we have the ARC, which is actually the system, which is the electronic health terminal system, where if a patient wants to get e-prescription online, then he can actually do it from home. He has sensors, he has everything needed to accomplish that. So this is to show you that in the ARC, in the medical emergency response system, there are social actors and infrastructure, and of course the software. This fits actually for our framework in order to use and come up with the security mechanisms. Because I'm sorry that we cannot read it, but this is about how it's all about the business process of the threat landscape in medical emergency response system. So I'm going to give you more on the adaptive security, how it works. So this is the architectural flow. The name of the extended version is Extra for us, which is actually an extended version of Asphalia. So let's say that we have a system under control. So this system, which is actually in our case, we took this MERS, a medical emergency response system. It's a critical, it's a critical infrastructure. It's also a good example of cyber physical system. It's a healthcare domain, so it fits actually our requirements, our motives, and so on. So and also actually it's publicly available resource from the Serenity project, so that anyone can validate and do also some analysis about that. So this, let's say that we have MERS, which is system under control. So this is a CPS, where it has these business processes, different business processes. So sensor, there is a component sensor that actually monitors MERS, our application. It monitors actually in case there are abnormalities, or what you call anomaly detections or unwanted behaviors. If the system is experiencing actually different unwanted behaviors. So the sensor is actually just fetching data, and then actually it sends a component called a security event evolution manager. So this security event evolution manager is responsible if the data sent by the sensors are actually in violation with our security requirements. So if a security violation, a security requirement have been violated, or if there is a need actually for evolvable security mechanism to our system. He wants to verify this. How to do that? There is a repository, which is, in the system we have this design time phase, runtime design phase. So we have a security model repository. So this security model repository is actually it's a component of the security models, the behavioral model, attack mechanism model, event models of Asphalia. Basically, this stores actually the 4 models. So this is actually a reference. It contains all these models, and then it looks if there is actually a reference that could indicate a violation of security requirement or security control that has been defined for the system, which is for medical, in our case, nurse. So, and then this security event evolution manager could trigger adaptation strategies if there is a need for an evolvable security mechanism. But what do you mean by evolvable security mechanism? Where you have initially you have a security mechanism that if your security mechanism is under some sort of attack or suspicious condition, then probably you might actually change at runtime. You did alternative mechanisms, which is alternative security solutions. So the adaptation strategy or adaptation model manager is responsible to translate these constraints that came from our security model repository. And then we have a behavioral model. This is typical, this what you call this feedback loop, right? It learns from the system, and then it captures actually the events under attack, and then it sends information. We use this Kalman filter algorithm actually to optimize different constraints. And then this model is responsible actually to send or to update the system. Okay, there is a new types of suspicious activities or incidents are happening, then this needs to be reported and updated, and then it sends to another component. We have another component called the MPC. This is actually a very good algorithm that we adopted from control theory, model predictive control. This model predictive control is actually responsible to optimize security solutions. This is sometimes like in a confusion state, because it has a solution, but it needs to optimize the security solutions in order to actually address for the suspicious activities that that was reported by the security event manager, and then and of course from the behavioral model. So this predicts or optimizes security adjustment based on the reference security goal that we have from our repository. And then it sends, of course, this actuator in order to execute the security or the alternative mechanism. And then finally, the actuator actually deploys or executes the solution, and then it sends to the system. So to make it actually summarize this all, I know it takes time to explain this, of course, but I just want to give you like a very high level what it looks like. So this is actually one iteration, one instance. So some events are actually one event happened, and then the system needs to go actually through this one iteration. So if something happens next time, and then it needs to go actually again the same loop. So this is the way how our framework works. So this closed loop architecture ensures that the system remains secure and resilient even under evolving threats and changing operational conditions, as long as it maintains actually the optimized security mechanism. To give you an example how the medical emergency response system have been applied in our framework, which is on the extra for us framework, let's say that we have indicators. So indicators, we call them, sometimes they are called also this situational awareness, but in our case we call them indicators. So indicator of security mechanism. So it indicates if your security mechanism is under some suspicious activities, or if it's failing, or if it's about to fail, or if there are some indicators. For example, for e-prescription, this is a single scenario from the nurse project. So we want to make sure that the e-prescription, where a patient actually requests online to get a medicine, we want to take care of actually one, data integrity, right? So there shouldn't be any temper during the exchange of, we want to make sure that the prescription actually needs to arrive to the patient without any compromisation. And then, of course, with the delivery speed. I just want to give you a little bit example. So ISM, which is indicator security mechanism of the data integrity, indicator of security mechanism of the delivery speed. So we have in formal methods where we call them this isotone, antitone. These are actually this, if they are directly proportional, inversely proportional. So in this case, let's say that you have a security mechanism. If you increase your encryption strengths, how do you increase your encryption strengths? It could be like cryptographic algorithms or the key size, it could be AES-128, AES-156. It's good if you increase actually your encryption strings. That means it improves your data integrity, right? But if you increase your encryption strings, it could be actually, negatively impact the delivering the e-prescription. So this has a negative impact. We call it anti-tone, but if it has actually directly proportional, we call them isotone monotonicity. The third one, the third indicator is, the second indicator is the authentication depth. I mean, this is a very simple scenario. You can use the single factor, multi-factor authentication, and so on. Increasing the authentication depth could actually harm the delivery speed, which is actually in delivering your e-prescription to your patient, right? But of course, increasing the authentication depth could have a positive impact in ensuring the data integrity. So in this case, the security properties are the data integrity. We have the data integrity and what we call the soft security requirements, which is actually the speed, because this is not a hard requirement, right? At least it's not under the CIA, this confidential integrity availability of the security property. Then for security mechanism, which is a secret solution. I mean, when I say security mechanism, that means it's a secret solution. So we have encryption and authentication. One case could be actually to maximize both, maximizing your authentication depth or your encryption strings at the same time. Okay, the system actually, the adaptation strategy could be to increase both, to maximize both security mechanisms, but this you might end up actually in failure case, probably unacceptable delays in e-prescription delivery. So here comes actually our model predictive control, which optimizes the security mechanism. This means it needs to take into account parameters. For example, if the data integrity drops below the threshold, then you can increase the authentication depth and the encryption strings. But if there is, if the delivery speed exceeds the maximum acceptable delay, then you should decrease actually the encryption strings or authentication depth. This is how our model predictive control component considers in selecting the optimized security mechanism. This is just a single entity from the medical emergency response system, which is actually the case of e-prescription, when a patient, requests online and to get it the medicine and so on. So what I want to, I would like to say that adaptivity or adaptive feature is is a way actually to make sure a resilient system, to make sure that your system or your critical infrastructure like CPS are resilient. So there needs to be a feature of actually adaptive security is one feature to make sure that your system is resilient. The second, now let me give you another different picture, which we are not actually an expert on this, but there is something that we can actually contribute. So these days, everything is actually everything is over-regulated. We have different regulations. For example, in that European level, we have this Digital Operational Resilience Act, and also standards like this NIST directives, NIST ISO standards, and so on. In the US, they have this HIPAA, Health Insurance Portability and Accountability Act. So I just want to actually map this regulatory requirements when we talk about cyber resilience in the age of in critical infrastructures or in cyber physical systems. All this critical infrastructure, for example, if we take in Sweden, all critical service providers by law they are actually, they need to be compliant with DORA, with Digital Operational Resilience Act. But these critical service providers are mostly related to these financial institutions like the banks, the insurance companies, and so on. And also we have this EU AI Act. Of course, companies need to be also compliant. And we have also other regulations that that all critical infrastructures need to be compliant. This is also an issue. So, for example, if we take DORA in Sweden, these critical service providers need to do pen testing every 3 years. This is like a huge, actually, burden to financial institutions because they need a lot of resources in order to accomplish that. But this aspect, LPT, trade-led pen testing, is one component of DORA. And then we tried actually to support, if we can do with our framework, LPT, basically CTI, cyber threat intelligence. So in the financial sector, there are these blue team, white team categorized under financial entity, which are board of directors, CISO, CEO, and so on. And then they have this red team, internal or external testers. And then there are threat intelligence providers. So here we want to actually contribute to the threat intelligence, which is CTI, using our frameworks, because our framework deals with monitoring of events, monitoring of threats, and then proposing security mechanisms. So this was like an extra contribution that we had with this regulatory component. This is how we address the initial scenario wizard, how to do TLPT. We try to use actually our vulnerability model in order to provide information or incidents to the threat intelligence. So we were acting as a threat intelligence providers, I would say, even though it's a very small project in this case. And then we use the attack mechanism model and the behavioral model just to do some attacking mechanisms. This is kind of like a testing. We thought this could help actually, or we could actually act as a red team, which is internal or external testers, and so on. So this is all in all, the cyber threat intelligence could enable compliance through early detection and automation that leads to cyber resilience. I think I have tried to give you a very condensed talk. That's it from me. These are the publication or references. Thank you so much.
Thank you very much, Elias, for your very interesting presentation. And dear colleagues, now we have time for question, answer, and comments. Welcome. You can ask using by our chat. Or... Okay, Jean-Pierre, welcome.
Thank you very much. Can you hear me?
Yes, we can.
Yes.
Jean-Pierre, your question?
Yeah. Yes. First of all, thank you, Professor Harshenko, for the invitation, and thank you, Dr. Elias, for a wonderful presentation. I learned a lot from your presentation. I want to ask a question about the use of AI in cybersecurity, specifically in critical infrastructure. For example, do you think it would be possible to have AI as a defense strategy or a defense mechanism when it comes to cyber attacks, and that AI will handle the incident response strategy, it's safe 100%. Let me paraphrase it. You know, we see, for example, now we have self-driving cars, the cars that drive themselves without intervention of any human being. Now, in critical infrastructure, presuming that there will be attacks, maybe AI-based attacks, do you think it will be possible to have AI acting as incident response strategy itself 100% without intervention of human being? I hope it's clear. My question is clear.
Thank you. Yes, the question is very clear. Thank you, Jane. Yeah, this has been a question of, I think we have been through this question for the last 4 to 6 months. Of course, we are in the AI where everything is migrating to AI, and then we should be positive about that. I am positive about AI, but in terms of using for incidents, actually monitoring, vulnerability detection, but even though actually we can use still AI techniques, but we need also to be very careful actually on these false positives. I tried myself now with this AI agent in Azure actually. I created that in order actually how it looks like, you know, vulnerability detection, automatic, fully automatic vulnerability detection. Well, in terms of time, you know, in terms of performance, efficiency, I would say it's very good in detecting actually. But what I have seen so far is actually, I'm not quite sure. I'm a little bit skeptical about the output. I mean, the quality of the output. Sometimes a lot of false positives, then consider them, they are really actually critical security incidents because it gives you a lot of data. That's why when I start my talk, actually, these two frameworks and tools are actually semi-automated. Intentional, they are semi-automated. We could have actually make them fully automated, but there needs to be human in the loop actually who could verify if these are actually critical incidents or not. Okay, you can get the results with the use of AI. I'm very totally positive about that, but I'm a bit skeptical about the outputs. You know, in security, we need data in order to train the models. Once we have actually sufficient data I mean, when I say data, it's not any data. In other disciplines, they are fine. They can train their models and they are fine. But when it comes to security-related data are very important to train. And having this, I would be positive about that. Once we get actually sufficient once we train our models, actually sufficient training is needed. That's what I could say.
Right. Thank you very much.
Thank you. Thank you. I see Professor Oliver Popov would like to add something. Welcome, Oliver.
Thank you so much. I don't have any more chance to examine him on normal exam, so let me ask a question. Thank you very much, Elias, for a very good presentation. And also, I must say it was a pleasure to have you as a PhD student. But having said that, can you give me an example of multi-connected or omni-connected system, which is resilient, the way you define the resilience, which is the normal way, all these 4 different functionalities which are important. Can you give me a good example?
So can you give, sorry, Oliver, can you give me a good example of what?
Of only connected or interconnected on a very large scale system, which is resilient as well.
So I would put it in different way. I think in my talk I have covered that the main challenge for these critical infrastructures, or for example in our case cyber physical system, they are actually designed in isolated manner. In a way that their components are actually isolated, but they work together. So these different, they are designed in piecemeal manner, which actually their components are isolated. This makes them actually, and then they interact actually in order to communicate. So this makes them actually a potential source of attack. So again, this is an issue, one issue that's in my opinion, this is an issue. And then again, to make a resilient system is actually, you could use features, for example, adaptivity technique is a resilience feature. And other techniques could also, AI techniques, for example, in incident monitoring, also vulnerability detection, even though I'm a bit skeptical about the output or the quality. So, well, you cannot actually, it's very hard to say that they are completely cyber resilient, because still they can actually get, the different attacks. I don't know, you can take the cyber physical system, for example, in the air control systems, even though they are resilient to different, external attacks, but still they need to maintain, to put it actually this way, as long as they anticipate, withstand, respond, adapt, and recover, and then they continue actually and consistently deliver their intended outcomes, then we can call them actually they are resilient. That's what I can say.
No, but there is an obvious example, Elias. This is the example that we are actually communicating on the top of this technology. It's called internet. Internet was made to be resilient. Internet was made to work in any situation, if there is a World War III or whatever. It was 50 years ago. What I would like to say is that we talk about, now it's become fashionable to say resilience or whatever, But this was a system which was based on two very important and very simple and very powerful protocols, or one of which is TCP, which is socially responsible by design. It, as you say, self-learning. It learns from the network, and basically it reacts and makes the network function in most situations, in most cases. Of course, there are failures and so on. So internet is an example which was made to be resilient in any kind of situation. And actually, for every resilient system like the internet or some other systems, that's the reason I ask you, the basic question you ask is how many failures or how many problems you're gonna have in your system, and you still call it an internet, or still call it the system as it was initially designed and initially intended. And that's one of the basic questions whenever you make some kind of a complex system or whatever. There will be failures, there will be problems, but you have to deal with them. And then there will be probably a point, a red line, where actually so many components of this system, as you said, piecewise designed or whatever, and so on, and fail. So you don't have anymore the system, whether you have a holistic approach or whether you have a technological approach or just a social or a combination of both, the system does not exist. So internet is a very good example of a resilient system, very good, and it's all more than 50 years, because somehow there was a sort of inherited congenital simplicity the way they were designed. And of course, they didn't think about all this resilience. They said, well, if there is a World War III, if there is a, God forbid, nuclear war or whatever, how many nodes of our network can fail and we can still communicate, get around and connect any two places on the network. And of course, they were thinking about military networks and defense networks and that kind of stuff, but doesn't really matter. The outcome was very positive for the mankind also in this case. So sometimes we look for, we make the things more complex than it is. We make them I mean, now it's, as I said, very fashionable to talk about resilience, to talk about AI and everything. Many of the problems in AI, we had them from the very beginning, in the 50s and the 60s of the last century, and they're the same. We shouldn't, I've been around for such a long time that actually we shouldn't make the difference between a sort of a formality and form, and between a competence and the essence, the semantics of what we are doing. You know, just to make a difference. It's occasionally, I think that there are how many, 70 or 80 researchers here, and it's very important for all of us to distinguish between something which is daily interest and trivial, and something which is gonna stay with us. You know, it's sort of invariant in many systems that we build, and so on. And actually, your title inspired me for this, you know, to do some thinking and that kind of stuff, which I very much appreciate, you know, the title that you had in interconnected world or omni-connected world or whatever. So my appreciations to you, Elias, and my appreciation to the audience as well. Thank you.
Thank you. Thank you very much for your question and for your comments. And dear colleagues, any question? I have one question to Elias. What about any specific metrics to measure, to assess cyber resilience in comparing, for example, with traditional cybersecurity indicators? I mean, how we can assess efficiency of such systems which you presented in comparing with other systems to better understand which specific benefits we have and how it can be measured quantitatively. Elias?
So sorry, I was unmuted. Yes. Oh, yes. Yeah. Thank you for your question. This is, I mean, interesting. We need to have actually different metrics in terms of the models. Actually, the quality of the models. It could be related also the efficiency of the outputs, and also the time actually to take to come up with different incidents in classifying them if they are actually security related events. And then actually optimization also. Optimization, it needs metrics related to quality, time, and also of course if they are semi-automatic systems, plus the humans are in the loop for the accuracy. So these metrics actually are in place, but again the metrics can be improved once we train them, like with a lot of security data. That's how we can, as long as we get actually sufficient security data, the metrics actually can be improved. So in terms of performance and the complexity of the models, and the time, effort, and other metrics as well.
Oh, okay, I see. Dear colleagues, any other questions or comments? No. Hence, let's thanks once more to Professor Oliver Popov and Dr. Elias Said for your presentation, for your interesting comments, and we wish you new success on your scientific and your industrial activities. Thank you.
Thank you so much.
Thank you, Slava.
Thank you. Okay, let's go ahead, and our next presenter, Ivan Ryabko. Ivan, do you hear me?
Good afternoon, everyone.
Yes,
Second.
you can share your screen.
Yeah, I guess. Did you see it?
Yes, we see and we hear you. Welcome.
Okay, good afternoon. Today we'll present a systematic approach to applying AI and machine learning methods for cybersecurity in medical web systems. Public breach reports consistently show that a large fraction of healthcare incidents is linked to web application and cloud services rather than purely on-premise components. Medical web platforms expose protected health information, imaging data, and critical clinical workflows via internet-facing portals and APIs, all under strict regulatory requirements such as HIPAA and GDPR and local legislation. This combination of high data sensitivity and exposed attack surface makes the domain particularly vulnerable. Classical security controls.
Excuse me? Excuse me, Ivan. We see just your first slide.
Yeah. It's okay. It's okay.
It's okay. Okay. Oh,
Yeah.
sorry. Well.
No. Oh, sorry. 1 second. Yeah. It's not okay. Okay. Yeah. Classical security controls is access control, encryption, network segmentation, domain essential, but they are increasingly inefficient against sophisticated and fast evolution threats. AI and ML methods can act as a force multiplier. They enable proactive anomaly detection, correlation of events across multiple layers, and reduction of time to detect and respond to incidents. In this talk, I will first map security tasks to appropriate ML model families, discuss valuation metrics and operational considerations, and then illustrate these concepts on a modular web platform architecture with integrated security analytics. Just a second. Okay. Yes. Before we dive into details, let me briefly outline the structure of the talk. I will start with the background and motivation, why medical web systems are an attractive target for attackers, and why purely classical security controls are no longer sufficient. Then I will present a conceptual approach, reference architecture for a medical web platform, and a parallel security analytics plane that collects and normalizes logs. In the third part, we will discuss AI and ML methods for security, how typical security attacks map to model families with metrics matter both for model evaluation and for operations, and what architectural and MLOps practice are needed to run these models safely. The fourth part is a platform case, a modular platform with PACS and OCHIF-based viewer, AI services, and integrated security analytics. Together with several concrete detection use cases, and finally I will summarize the main takeaways and outline directions for further work and potential collaborations. Yes. Okay. Before going deeper into methods and architecture, let me briefly situate this work within existing literature and standards. On the web and application security side, OWASP Top 10 remains a practical reference for common vulnerabilities in API-driven medical portals and integration services. At the management level, ISO IEC 27001 and related controls provide a structure for information security risk management, which many hospitals and vendors already follow. For healthcare-specific guidance, the HIPAA security role and the documents such as NIST SP 856 emphasize access control, audit logging, and incident response in clinical systems. In AI-assisted monitoring, we propose must ultimately align with three requirements. One, the architectural side, NIST SP 800-207 formalize zero trust principles that we adopt as a baseline assumption rather than a novel contribution. Finally, the NIST AI Risk Management Framework offers a language for trustfully AI covering governance, validity, robustness, and transparency. My goal in this work is not to invent a new standard, but to connect concrete AI methods for security with this ecosystem of existing best practices and regulatory expectations in the context of medical web systems. Okay. The core contribution of this work is a systematic mapping from security tasks to ML model families with concrete technical rationale. For anomaly detection in access logs, the complex events or API traces, we need unsupervised methods because labeled attack data is scarce and new attack patterns emerge continuously. Isolation forest works well on high-dimensional feature vectors extracted from logs, for example, aggregating request counts, response times, and error rates per user, IP, and endpoint over time windows. One class SVM can capture non-linear decision boundaries when normal behavioral clusters in complex shapes. Autoencoders, especially LSTM-based variants, excel at learning sequential patterns. They can detect when an API call sequence deviates from typical workflows, such as a radiologist assessing the studies in an unusual order or at untypical times. For classification of known attack types, say SQL injection patterns for no malware signatures, supervised models are more appropriate. Random forest provides interpretable features importance, which helps security analysts understand why an alert fires. Gradient boosting methods like XGBoost often achieve higher accuracy but are less interpretable. For text analysis, BERT-style models can understand semantic context. They can distinguish between legitimate password reset requests and phishing attempts that mimic legitimate language. Finally, for user and entity behavioral analytics, graph neural networks model relationships. A user account connected to multiple devices assessing cursors across different network segments forms a graph. GCNNs can learn to identify when this graph structure changes in suspicious ways. For example, when a user device graph suddenly includes a new unknown device from a different geographic region. Sequence models complement this by learning temporal patterns. If a user typically assesses packs during business hours, but suddenly starts assessing at 3 a.m., an LSTM-based model can flag this as anomalous even if each individual access looks legitimate. Before we talk about operations, let me fix terminology for ML evaluation itself. In offline experiments, we care about true positive rate, how many real attacks we catch, and false positive rate, how many benign events we flag incorrectly. Precision tells us what fraction of our alerts are actually attacks, while recall tells us what fraction of attacks we detect. F1 score balances these two, and ROC summarized the performance across all possible thresholds. The ROC curve visualizes this trade-off. As we move along the curve, we gain sensitivity but pay with additional false alarms. A point in the middle of the curve can be interpreted as a balanced threshold, while a point further up and to the right corresponds to a high sensitivity regime, when we catch almost all attacks but accept more false positives. This picture is important because every operational choice later, how aggressively we want to alert, corresponds to picking a point on this curve. Okay. In production, stakeholders really talk about ROC directly. They talk about how quickly we detect and contain incidents and how much friction we add to clinical workflows. Mean time to detect, or MTTD, captures how long an attack can persist before we notice it. Mean time to respond, or MTTR, measures how quickly we can contain it once detected. The latency overhead is running ML models must be small, typically well below 100 milliseconds per request, so that radiologists and clinicians do not even feel that security analytics in there. System availability must remain high, often above 99%, which means ML components cannot become a single point of failure. Perhaps the most dedicated constraint in analytics workload. If the false positive rate is too high, analytics are flooded with alerts and start ignoring them, which defeats the purpose. Increasing sensitivity to catch more attacks inevitably produce more false alarms, and complex deep learning models, while accurate, can be harder to explain to auditors and clinician stakeholders. The practical lesson is that we need to tune models with both ML metrics and these operational constraints in mind from the outset. Any assisted security workflow begins with disciplined data engineering. Logs from different sources are fundamentally heterogeneous. Web server logs from Apache or Nginx contain HTTP request response pairs with timestamps, IP addresses, user agents, and status codes. The complex audit logs record study access events with DCOM UIDs, user identities, and actions like retrieve or query. Network packet captures can be aggregated into flow records showing source and designations, IPs, ports, bytes transferred, and protocols. To enable ML models to correlate events across these sources, we must normalize them into a unified schema with consistent identifiers, timestamps, and contextual metadata. Feature engineering then transforms raw log entities into numerical vectors suitable for ML. Temporal features capture time of day and day of week patterns. For example, a radiologist accessing PACS at 3 a.m. is unusual if their typical pattern is 9 a.m. to 5 p.m. Aggregations over sliding time windows create behavioral features. Request counts per user per endpoint, average response time, error rate, session-based features capture access patterns, how long a user session lasts, which endpoints the access in sequence. The outcome of this tip is stable, ML-ready feature space that later models for anomaly detection or UAB can operate on. Because healthcare data is highly sensitive, any security analytics pipeline must respect privacy by design. Data minimization means logging on only the fields that are necessary for detecting security events and hashing personally identifiable information such as patient identifiers or user mail address. When we want to benefit from cross-individual data without centralizing logs, federated learning is an attractive option. Each hospital trains a local model on its own data and shares only parameter updates with a central aggregator which computes a global modeling and redistributes it. Raw logs never leave the site. Differential privacy adds another layer of protection by injecting calibrated noise into aggregate statistics or model updates so that an attacker cannot infer whether any individual record was part of their training set. In this work, I treat federated and differentially private training as a methodological directions that can be pursued when data governance and infrastructure allow it, rather than as assumptions about an already available dataset. AI/ML methods for security are only effective when built on a robust architectural foundation. Zero Trust is the organizing principle. Instead of assuming that anything inside the network perimeter is safe, we continuously verify every user, device, and service. Users authenticate with multi-factor authentication and device certificates. Services communicate over mutual TLS, and a service mesh enforces policy at the application layer. Data flows are encrypted in transit and at rest. Network and application level segmentation enforce least privilege access. Users can only reach the resources they need for their route, making lateral movement by attackers much harder. Role-based access control ensures that a radiologist can access imaging studies but cannot modify billing records. anti-detection and response platforms, or XDR, correlate events from multiple sources. Endpoints like workstations, network infrastructure, cloud services, applications, and PAC systems into an unified timeline. This correlation is essential because a single event in isolation might look benign, but a sequence of events, for example, a user logging in from an unusual location, then immediately querying a large number of patients' records, may indicate an attack. SOAR platforms automate incident response when an ML model flags a suspicious pattern. A playbook can automatically isolate the compromised account, revoke active sessions, and notify the security operations center. Finally, comprehensive observability is a prerequisite for ML. We need structured metrics for monitoring system health and distributed tracking to understand request flows. Without high-quality telemetry, even the best ML models cannot provide reliable security signals. Okay. Security ML models are not one-off experiments. They are long-lived products that interact with clinical workflows and regulatory frameworks. MLOps practices provide the structure for managing the life cycle. Versioning is critical. We must track which training dataset was used, which feature definitions were applied, and which model artifact was deployed. Tools like DBS and MLflow helps manage data and model versions. The features store centralized feature definitions so that multiple models can share consistent features and we can reproduce results. Documentation through model cards communicates essential information to both engineers and auditors. What the model is designed to do, what data is trained on, what its performance characteristics are, and what is known limitations are. For example, a model card might state that an anomaly detection model was trained on logs from a single hospital over a specific time period, achieved certain performance metrics, but may not generalize to hospitals with different workflows. Continuous monitoring is essential because the environment evolves. User behavior changes, infrastructure is updated, and attackers develop new techniques. Concepted detection uses statistical tests to identify when the distribution or incoming data deviates from the training distribution, signaling that the model may need retraining. Performance monitoring tracks accuracy degradation and latency increase. Fairness monitoring detects if models exhibit bias. For example, if false positive rates are significantly higher for users in certain geographic regions or with certain roles. Deployment must be controlled and reversible. Stage rollouts gradually increase the fraction of traffic handled by a new model, allowing us to monitor its impact. Canary deployments run a new model on a small subset of requests and compare metrics against the current model. Automated rollback mechanism revert to the previous model if error rates exceeded thresholds, ensuring that clinical operations are not disrupted by faulty models. To make these concepts concrete, let me describe modular web platform architecture that integrates security analytics in a first-class component. The application layer provides the other interface, an Archive-based DCOM viewer that runs entirely in the browser, requiring no client installation. Radiologists assess worklists showing studies assigned to them, and the web portals serve both patients and clinicians. RESTful APIs expose functionality for querying studies, retrieving images, and invoking AI inference. The data layer consists of a PACS archive. We use our tank as an example. Through any DCOM-compliant storage works that stores DCOM objects. A PostgreSQL database holds study metadata, user session information, and audit logs. DCOM Web Services provide standardized interface for storage, retrieval, and query operations. The AI service layer is modular. Each AI capability, such as bone age estimation, pneumothorax segmentation, or fracture detection, is implemented as a separate microservice with its own API endpoint. A service mesh managed the communication between service and enforce policies. A model registry tracks versioned AI models and their inference endpoints. The security analytics plane is the key innovation. It ingests logs from all layers, web server logs, IP gateway, events, PAX audit logs, and AI service logs. Normalize them into a unified schema, extract features, and runs ML models for anomaly detection, UEBA, and attack classification. Results are exposed through dashboards for security operations and real-time alerting. The architectural insight is that security analytics is not an afterthought or a bolt-on component. It is a parallel plane that reuses the same identified logging and observability mechanism as clinical models, allowing it to evolve independently while maintaining consistency. Okay. Let me illustrate how security analytics operate in practice with three concrete use cases. First, anomalous access pattern detection. A radiologist typically assesses PAC studies during business hours from their office IP address. An isolation forest model trained on historical web access logs learns this pattern. One night, the same user account assessing studies from a new IP address in a different location and at unusual time. The model flags this as anomalous because its derivatives from the learned normal distribution is both time and location dimensions. A UABA sequence model complements this by analyzing the access sequence. The user queries an unusually large number of studies in a short time period, which significantly exceeds their typical access rate. The combination of these signals triggers an alert, suspicious access pattern, possible credential compromise. The security team can then verify this legitimate, perhaps the radiologist's on call, or if the account has been compromised. Second, API abuse detection. An autoencoder trained on API gateway logs learns to reconstruct normal request patterns. During a DDoS attack, an usually high volume of requests per minute target the same studied retrieval endpoint from multiple different IP addresses. The autoencoder's reconstruction error spikes because this pattern does not match learned normal behavior. A random forest classifier trained on known attack patterns identifies this as a DDoS attempt. SR playbook automatically rate limit the offending IP address and notify the security team. Third, insider data exfiltration. A graph neutral network models relationships between users' resources, in this case, DECOM studies and devices. A user who typically downloads a small number of studies per session suddenly downloads an unusually large number of studies in a single session. The GNN detects that this creates an anomalous subgraph. The user node now has edges to many more study nodes than normal, which is far outside the normal distribution, correlating with PAX audit logs, confirming bulk retrieval. An alert is generated, potential data exfiltration, bulk study download. The security team can investigate whether this is legitimate, perhaps for a research project with proper authorization or unauthorized data exfiltration. These samples demonstrate how ML models operating on normalized multi-source logs can detect traits that would be difficult to identify with static rules alone. To conclude, this work presents a systematic approach to applying AI and ML methods for cyber security in medical web systems. The key contributions are fourfold. First, a systematic mapping from security tasks to appropriate ML model families with technical rationale for each choice. Second, architectural patterns, zero trust, XDR, SOR, and comprehensive observability that provide the foundation without ML cannot be effective. A third, MLOps practice for versioning, monitoring, and control deployment that ensures security ML models are treated as long-lived governed products rather than experimental prototypes. fourth platform case study demonstrating how modular architecture can integrate security analytics as a first-class component. First-class component. Yeah. So looking forward, several directions are promising. Federated learning palettes could enable cross-institutional collaboration without centralizing sensitive logs. Explainability toolkit integrating SHAP or LIME could help security analytics understand why models flag specific events, improving trust and compliance. Integration patterns with hospital security operations center workflows could streamline incident response. Finally, real-time streaming ML pipelines using technologies with Apache Kafka and Flink could enable sub-second tree detection, reducing MTTD for minutes to seconds. I welcome questions and any discussions. Thank you.
Thank you, Іван. Дякуємо. Welcome your questions. До речі, шановні колеги, я не сказав, ви можете задавати запитання, звісно, українською мовою, без всяких проблем. Можемо проводити переклад, так що, будь ласка. Ваші запитання. Ну, поки всі міркують, let's come to slide 6, where you talk about trade-off. Please, more detail say about which elements of trade-off we have here. I see sensitivity, yes, which one? Next, please, your comment.
Yes. You mean explain more about it, or for example,
Коли ми говоримо про трейд-офф, так, ми говоримо про певні конкуруючі характеристики, так? От які саме характеристики тут є конкуруючими, я не зовсім це зрозумів, так? Ну, в контексті безпеки ж тут, я так розумію. От.
MTTD and MTTR, here conflict. High certificate component. I guess sensitivity versus specificity, yes, because higher sensitivity push us to favor missed attack but more false alarms, yeah. And higher specificity favor false alarms but more missed attack. Or even precision versus recall. Like higher precision alerts are more accurate, but you may miss incidents, and recall follow you to detect more incidents, but alerts accuracy might drop. Something like that.
Okay, and next question, this related to this slide. You talk about high availability of this system, more than 3.9 after comma. How such high level of availability can be reached in this system? I mean, in point of view reliability, in point of view security, or any other attributes.
Achieving this availability requires eliminating single points of failure at every layer and ensuring the system can survive component failures. It's like redundancy on either tier, multiple web servers, replicated application servers, also database replication, and redundant storage. Load balancing also and traffic distribution.
Okay, hence in this case we use traditional means for cloud and other kinds of systems.
Yes, because ML model can catch traffic in a couple of milliseconds, then proceed it in 1 or 2 seconds, and that's it. So.
Okay, and please slide 10 or 11.
Just a
I don't
second.
remember which one.
This one. Or...
No. Yes, this one. In this case, we thought about AI service layer and AI modules. Why AI-based decision is required here? What is the reason application AI?
Application AI, it's about only security level, yes?
Yeah.
Because just because in basic case, security team cannot see everything in the system because it's huge traffic and it's can be reach everything. But ML models can find can watch every service in this model. So security team just can waiting for alerts and answering on this. Yeah.
Okay, and can you say something about specific vulnerabilities of these AI modules?
Vulnerabilities.
Or it's important in general. I mean,
Guess maybe model poisoning, but when you work accuracy, I don't think so. It's possible. Maybe evasion attacks, like attackers can craft requests or access sequence that exploit decision boundary weaknesses. But because we're using AI models only for watching, we don't using AI models for decision making, so it's okay.
I can say is such vulnerabilities can be not very critical. Yes.
Yes.
Okay, thank you.
Because we use ML only for statistics, so it's not so critical. Yes.
Okay. Any other questions? Будь-які ще запитання, шановні колеги? Так, не бачу, не чую. Тоді... Okay, let's thank Ivan for your presentation, and we wish you go ahead with your research and development.
Thank
successfully.
you. Thank you.
Okay, thank you. And dear colleagues, we go to our finish. I would like to add some information about our events which were before today meeting and will be next weeks and the next months. So, 1 minute. Я вже українською далі буду говорити. Ну, впродовж останніх тижнів було доволі багато різних подій, які пов'язані були з питаннями кібербезпеки, захисту критичної інфраструктури. Зокрема, 3-4 листопада в Києві відбувся Київ International Critical Infrastructure Protection Forum, який зібрав багато спеціалістів з різних країн. Ну, я мав честь там представляти ХАІ і брав участь в одній з панельних дискусій стосовно кіберзагроз для об'єктів критичної інфраструктури разом з колегами з Польщі і Сполучених Штатів. Ну, на цій панельній дискусії була ще раз прорекламована от наша спільна робота з колегами, так, яка навіть отримала таку підтримку одним з конгресменів Сполучених Штатів, і надіслана була пропозиція стосовно її використання як елементу екосистеми для підготовки спеціалістів. Зараз ми готуємо другий випуск цієї книги, і це буде, я думаю, доволі швидко зроблено. Так. Далі. Ну, далі позаминулого тижня відбувся також цікавий дуже захід в Варшавському університеті, де були презентовані американо-польсько-українські програми для подальшої співпраці. Є посилання на всі презентації, які були на цьому форумі надані, на цьому тренінг-заході. Так що можна з цим ознайомитися, шукати партнерів і рухатися далі. Ну і ще один день була дуже цікава подія в Польському національному науковому центрі з ядерних досліджень, де ми презентували результати наших розробок, ну, а перш за все розробок корпорації Радій, які базуються на відомій сертифікованій американським ядерним регулятором платформи Radix. І ну, в Польщі зараз будується перша станція атомна, тому ну, тут може бути відповідна співпраця. Так, перепрошую. Так, і ще одна подія закінчилася буквально от позавчора. На базі нашого університету прийшла міжнародна конференція Integrated Computer Technologies and Mechanical Engineering. Ну, доволі потужно була представлена ну, громада, так би мовити, з інформаційних технологій. Ну, а кафедра наша фактично от курувала проведення секції Cyber Security, Internet of Everything, і модерував доцент Перепеліцин Артем Євгенійович. Ну і крім того, доцент Куланов Віталій Олександрович модерував секцію от Control System and Testing. Так, дуже важливо, що виступило багато наших і аспірантів, і студентів, і в цілому, мені здається, це була дуже корисна і цікава подія. Конференції, які в цьому році ще відбудуться, вони вже фактично їх залишилося от дві в цьому році, так, і та, ну, яку ми опікуємо вже доволі давно, знаєте, це конференція «Десерт», зараз закінчена фактично вже прийняття доповідей, більше 120 доповідей отримано, будуть цікаві кейнот-спікери, тож долучайтеся, і 19-21 грудня цю конференцію будемо проводити в Афінах на базі центрального дому грецьких збройних сил, офіцерський клуб, там доволі гарні умови для проведення конференцій, тож є можливість долучатися як і слухачам, і як учасникам. Так. І продовжується робота нашого науково-технічного семінару аспірантського, молодіжного, з грантоздатних інформаційних технологій, йдуть заслуховування таких доповідей по середах. І ще я хотів би теж анонсувати, наступного тижня буде студентська конференція з інформаційної функційної кібербезпеки. Це 5-та вже за останні роки. Так, вона вже стала де-факто, то й стає де-юре міжнародною. Її організують наші колеги, це професор Певнєв, доцент Землянка і аспірант Юдін. Тож теж доволі багато доповідей, там, мені здається, більше 90 є, так що 27-28 запрошуємо. Ми будемо, я звертаюся до всіх, ну і хто в Харкові зараз знаходиться, будемо цю конференцію проводити з нашого захищеного простору. Тож 2 дні цікавої роботи нас чекають. Так, а напередодні буде проходити ще один такий конференція, невелика семінар з проблем резильєнтності і захисту об'єктів критичної інфраструктури. Тут теж будемо проводити в нашому захищеному просторі. Ну, і далі я хотів би проанонсувати ще нашу наступну зустріч в грудні. It's my pleasure to invite you to our next meeting of our seminar. We will hold this seminar 12th of December. We plan to organize 2 presentations. First one from our Harkiv National University of Karazin. Will be dedicated to application AI means for analysis of information in media and so on. And other presentation will be connected with application of augmented reality and AI in interactive art. And we will have possibility to hear presentation of painter Alena Galimbovska, and I think it would be a good event, good interesting event for the finish of this our seminar year. Hence, such program of our December activities. If you have any questions, I would like to answer. Шановні колеги, на цьому наш порядок денний вичерпаний. Давайте ще раз подякуємо нашим доповідачам. Thank you so much, професор Oliver Popov, Dr. Elias Said. Thank you very much, Ivan Ryabko, and welcome to our next meeting, to our next activities in our cooperation. Sorry, I cannot switch on my camera because electricity is not good. Hence, I can send just by without camera. Тож, дякуємо ще раз. Дякуємо, Elias, Oliver, and all colleagues. Today, more than 70 participants joined to our seminar. Thank you once more. Thank you, our students, our lecturers, and our colleagues from different countries. Thank you very much.
Thank you very much, Slava. We will always gladly, when we are welcome, to participate in your seminars, and I wish you all a very nice weekend.
Welcome. Now we have electricity, and hence I can switch on my camera. Okay.
No problem. No problem.
Okay. Thank you very much once more, and see you.
Thank you, guys.
See you. All the best.
And sorry for some technical problems.
Yes, of course. I also had problems in the beginning.
Okay. Mm-hmm.